Okay, let's get started. So, what's due this week? Homework 1. Any questions on homework 1? Okay, so so the second homework should be out by Wednesday and then due a week later, just like homework 1 was. Okay, so what were we talking about at the end of last time? Yeah, this thing called the Powerset construction. But what is it for? What are we actually trying to do with it? Yeah, I have no idea why that screen's not working. We'll try to get it fixed before Wednesday. You'll have to look over here, sorry. Yeah, so we're trying to make I don't know who said it, a DFA from an NFA. So the process is about the NFA to DFA conversion. Cool. So we started working on an example last time. So let's do it in full generality. So let's let N be an NFA. And let's actually give the pieces of the NFA a name. So it has some states, sigma, transition function, Q0F. Be an NFA. So there's one thing that I should mention. For the transition function for DFAs, what were the two pieces of information that you needed to know for a DFA, for the transition function? Yeah. So the state that you started at, the character that you read, and it gives you the state that the transition goes to. Well, for an NFA, we augment the definition of transition because we have these two weird situations, right? Where we can have a state on the same input going to two different states, and we can also leave some out, but we can also have epsilon transitions. So what was this epsilon transition thing? Not quite. It's like that.
You can take the transition without reading input.
Yeah, you take the transition without reading anything. Yep. So this is just more of a side note than anything else. So the way that transition functions work with an NFA is that we're going to write it as QX, where Q is a state of the set of states, but X is an element of sigma union the empty string. Okay, so it's before with DFAs, the thing in the second argument was just an element of sigma, the alphabet. Here, we can have either a character from sigma or epsilon, which corresponds to an epsilon transition. And this will give us a subset of Q. So if I give you the state and the either input character or epsilon, it'll give us back, instead of one state, it'll give us a set of states. Whether that set is empty or every state or one state or anything, it just gives us a subset. I could define it more precisely, but I think this is pretty clear. So it's a state then either a character or epsilon, and it gives us a set of states because we can have multiple transitions on the same symbol to any states that we want. Okay, so let's actually construct a DFA. So we will construct an equivalent DFA. So I'm going to call it D for Dougherty, obviously. Then the set of states I'm going to call Q prime. The alphabet is exactly the same. I'm going to call the transition function delta prime, Q0 prime, and F prime. The alphabet doesn't change, so there's no point in priming it. Okay, so let's figure out what to do then. So what was our big idea with the states when we started to work on this? So we were representing states in the DFA as what in the NFA? What were we representing them as? And how did we relate them to the states to each other?
Ordered pairs.
That was for the product construction, yeah. Whereas with the NFA, we had the Q0, Q3, I think, state. And then after we read the 0, I think, we could be in either Q1 or Q2, and then when we read another character, we could be in Q0 or Q3. So actually what we were doing is we were having the states of the DFA be sets of states of the NFA. So like in the example we had Q0, Q3 represent a state in the DFA, and another state, Q1, Q2, be another state of the DFA, and we related them via transitions. So, in fact, in general, we may need every single possible subset. So what is the set of all possible subsets of something? Powerset. So that's actually where the name Powerset comes from. So the states of the DFA, we might as well just put every subset in. So I'm going to have it be the power set of the NFA states. Which is quite a few states. If I have 10 states in the NFA, this method will make 1,024 states. Do we necessarily need all of them? No, in fact, we did an example last time where we had only 3 and that were necessary and the other 13 were unreachable. But in general, I might need all of them. Okay, so we're gonna take a little bit of a detour because to explain the other pieces. So I'm just going to put a little thought bubble over here. Okay, so when we had the when we were working with that NFA we were working with last time, we thought of the start state of the DFA as something like this. So in the NFA we had, say the start state was here, and then it had some transitions that did whatever, but we had this epsilon transition to Q3, which may or may not have other transitions. And in this example, can DFAs have epsilon transitions? No, they can't. So what would the start state of the DFA represent from the NFA? Where are the possible places I can start in the NFA? Q0, Q3. What if I had another epsilon transition to another state, let's just say Q2? What would...
Yeah, it would be Q. It would be the same thing, but also Q.
Yeah, so it's basically Q0 along with any place we can reach with only epsilon transitions from Q0. So I need a definition in order to utilize this properly. Let's see. I'll remove the bubble so I can actually have some room. So we're going to call the epsilon closure of a set of states X is the smallest subset Y that has two properties. One, X is a subset of Y, and two, if there is a Q in Y, a state in Y, Q in Y, and epsilon transition from Q to Q prime, then Q prime is also in Y. Yeah, that's right. Okay, I thought I missed one of the technical terms. It's right. So the basic idea is you have a set of states X, and you, from those states, just go as far as you possibly can, only on epsilon transitions and nothing else, just from those states. So the epsilon closure of just Q0 in this example is, well, it has to have Q0 in it, but it also will contain Q3 and Q2. You go as far as you possibly can only on epsilon transitions. So for our equivalent DFA then, what should the start state of the DFA be? Well, we need to start at the start state for the NFA and go as far as we possibly can on epsilon transitions only. So what should it be in this case? Well, it has to do something with epsilon closure, right? Yeah, so it's the epsilon closure of the NFA's start state. So the start state of the NFA, and go only from that state as far as you possibly can on epsilon transitions. So for this, we're going to denote this as E of X. So E of X means the set of states X, and we take the epsilon closure from that. That means E of X. So I'll actually help you out with the start state for the DFA. That is the epsilon closure, so E of the singleton set Q0 and nothing else. So in English, this is just going from the start state of the NFA, taking the epsilon closure of that singleton set, which means just go as far as you possibly can on epsilon transitions. Okay? You have a question?
Will we be able to draw this later as a DFA?
What do you mean by draw it?
Because it's Q0, right? We have to eventually like map out the DFA.
You mean do an example, or?
We can wait. Just.
Okay.
I think we'll get
Okay, that's fine. Let's do the transition function. So here, what does the transition function of a DFA do? What does it take in?
Takes in a start state and input it and gives the next state.
Right, it takes a state, input, gives us a state. Well, the states of the DFA here are sets of states in the NFA. So I'm going to write this as X representing a set of states in the NFA with some input A. Okay? Well, then what do? So let's just do a small picture. So suppose that X is Q2, Q3, and I have a state Q2 here on A, maybe it has two of them, and then Q3 also has a transition on A. And they go to states, I don't really care about them. So in order to figure out what are the possible states we could be in after this, what was our idea of approaching that, of keeping track of every state we could ever possibly be in? Well, what we did was we looked at Q2 and we said, where do you go on input A? And then we marked down all the possibilities. Then once we do that, we look at Q3 and then figure out where it went on input A, and then just put all those possibilities together. So like for example, so if this was Q4, Q5, Q6, then the resulting set of states that I could be in are these three states. So the set of states I keep track of now is Q4, Q5, Q6. If this is the situation that we're dealing with. So how would we actually handle this? Well, what we do is, well, since we're dealing with a set of states in the NFA, we just figure out what the NFA did on one state, and which is a set. Then we look at the places where we can go from the second state, it's a set. Third state, it's a set too. And then once we've done, we union all of the resulting states we could be in all together. So in fact, what we're going to do here is we're going to union for every state Y in this set X what the NFA would have done from that one state. So the NFA's transition function is delta, no prime. So I'm going to feed that the single state Y, just one of the states in my collection, on the same input. I know it looks horribly confusing and it's about to get worse, but we'll do an example in a sec. So all we're doing is we have a collection of states we could be in, and then we just figure out from each one what the NFA would have done, and then collect all of the results together by union, because the NFA's transition function gives you a set of states. So if you want to collect everything together, you got to union all the sets together. But what could happen in addition to this is look at the Q4, Q5, Q6 things. Could it be that there's an epsilon transition to, say, Q7 over here? Yeah. So once we have these three states, what do we have to do in addition to include other states? Yeah, do the epsilon closure of that whole set. I'm going to keep it blue. So epsilon closure of this gigantic mess. And that's the end of the transition function, so it won't get worse. But yeah, I know it looks complicated, but the idea is really simple. You just work with each state individually, collect all the results together, and then do epsilon closure once you're done with that. Cool. So we're done converting to a DFA, right? Oh, final states. Okay, well, let's see. So let's just say, for sake of argument, that Q5 is a final state. So if we were observing this Q4, Q5, Q6 as a single state in the DFA, should it be final? If it was Q4, Q5, Q6? Yes. Why? Why should we make that a final state? It is the right answer, but why? Because think about how an NFA works. It will make a choice if it's possible to be accepted. So if Q5's in our collection of states that we could ever be in, there must be a set of choices that leads to one of those final states, Q5, for example. So the final states of the DFA are the sets of states in the NFA where at least one of them was originally final. So we can actually write the set of final states pretty easily. So the final states of the DFA are the subsets X of the NFA, all the sets of states we could ever possibly be, where the intersection between the observed subset and the original final states is not empty. So I'll actually write this in plain English. So this means at least one element of X originally was a final state of the NFA. So if we had Q4, Q5, Q6, well, one element was a final state, Q5, so therefore we will mark it as final in the DFA. Okay? If we had Q2, Q3, neither of them is final, so therefore in the DFA that pair of states would not be a final state. Any questions on that? Unless you want to do an example. I think an example is warranted. So here's an example. So let's make it a little bit non-trivial. One of the hazards with making NFAs is that in the conversion, it may be possible that the machine actually just accepts sigma star, and so then you have every state being accepting, but let's actually try to force it to not be. Okay, I think that's sufficiently complicated. Yeah, that shouldn't be too complicated. Yeah, okay. I'm trying to do the construction in my head, and it's sometimes hard to do. I want to see how much work it would actually do to make this. Okay, so if we just applied the Powerset construction just directly to this, there are 4 states in this guy. How many does the Powerset construction give us? So how big is the Powerset of a set of 4 elements? 16. So If we just applied it naively, we would have 16 states. So is there a better way to making a DFA? Yeah. What was the method I called it last time? It was the build states as you go method. So instead of making everything all at once, we just build the states as we need them. Okay. So let's make a DFA. So here's the NFA. Let's make a DFA. So what do we have to do at the start? Yeah.
You have to do the empty state.
The start state of the DFA, right? Well, what will it be in this case?
0 and 1.
Yeah, Q0 and Q1 because we see an epsilon transition over, and there's no other epsilon transition, so that's all we need to do. So I'm going to denote this by Q0, Q1 as a set, and that's the name of the state. So Q0, Q1 is the name of the state. Okay, so now we got to figure out where we can go on input A and input B. So where can I go on input A from Q0, Q1? I can go to 2. Where else can I go? Q1 because of that self loop up there, and that looks all we can do. Now, what is the epsilon closure of Q1, Q2? Can we go anywhere else? No. So we have to include those two states, but we can't go anywhere else. So, and we don't have that state yet. So I'm going to make a new state, Q1, Q2. So that's a new state. And then I'm going to have that transition be A, of course. What about on input B from 0 and 1?
No.
Nowhere. So what is the set of states that Q0 goes on input B in the NFA's perspective? It goes nowhere. So what is the set of states that you go to? Empty set. What about from Q1? Also the empty set. Well, what does the Powerset construction say to do? Take those results and union them together. Well, what is empty set union empty set? Empty set. So that's why we had that empty set state before. So this will be empty set. And I'm not going to go through it again, but the empty set state is a quote-unquote dead state, so you would have a self loop on A and B. Okay, so that's nice. So now we have only one branch to consider now. So, which is the Q1, Q2 branch. So where can we go from Q1, Q2 on input A? Well, Q1 goes to itself and Q2.
So it loops on itself.
So it loops, it's a self loop. Nice. So now we only have one branch to consider now. So where do we go on B? 2 goes to 3, Q1 goes nowhere. So empty set union, the set which just has Q3 in it, which is Q3. And there's no epsilon transition to consider, so it's just Q3. Always remember, so here's a pro tip, always remember to do epsilon closure at every single step of the way. It's just a good habit to get into. Okay, so Q3 is where we go now. What about Q3 on input A? So it goes to Q0, Q1, because it has 2 transitions to those. Now what about epsilon closure? So we're in Q0, Q1 now. Yeah, it's already included. So we already have that state, Q0, Q1. Nice. So we get to close this branch. Oh, what about the B for Q3? So Q3 on input B, where can we go? Just to self. And there are no epsilon transitions. And that's it. This example actually did work well. Happy about that. Okay, what about for final states? Which of these states should be final?
Q1, Q0, Q1, Q2.
Yeah, so it's any state that has Q1 in it, because it was the only final state before. So this top state needs to be final, and the next state needs to be final. Q3 doesn't have Q1 in it, so that's not final. Empty set doesn't have Q1 in it, so therefore it's not final either. Nice. Is that clear or bad?
Yeah, but it's okay.
I can fix that. But are there any questions on that? Is that a little bit better?
It'll do. Not much, but it'll do.
I'll try to explain every pixel that I draw, and that might help. Okay. Any questions on the method, though?
So for Q1, Q2 on input A, so Q1 go back to Q1, Q1, Q2.
Yeah, because there's no transition from Q2 on input A, then we don't, because Q2 doesn't go anywhere on A, that's just the empty set of states. Whereas Q1 can go to itself in Q2, so we have the set Q1, Q2, union empty set. And so it's just Q1, Q2. Other questions? Yeah.
If we had an epsilon connection from Q3 and just to Q4, and then had Q4A back to Q0 as well.
Hold on. So we have, this is what you're saying, so Q4.
Had that epsilon A connect to Q0,
And
then have that B connect to itself. All we would have to do is put Q4 into Q3 in the DFA.
yes.
Okay.
Yeah. Because Q3 and Q4 are what are called equivalent states. So we haven't talked about this and probably won't, but there's a notion of equivalence with respect to states. If two states with their outgoing transitions go to the exact same places, then they're equivalent. These aren't exactly equivalent because Q4 doesn't have a transition up to Q1 like Q3 does, but because there's an epsilon transition in there, you can say that they're the same state. Yeah. Whereas if because of that. Now Q4, it doesn't need a self loop because Q3, if you read a B, well, Q4 goes nowhere. Q3 will go back to itself, but then epsilon closure will include it anyway. So you're right. You would just include Q4 and the DFA would be exactly the same. Cool. Other questions about this? Yeah.
If the alphabet also contained a C in it,
Mm-hmm.
would you just make the transition from empty state to the...
Right, you would, because we're making a DFA, so you would need a transition on every character. If the NFA didn't have a C at all in it, then the DFA on that input C would just go to the empty set state, because there's no transition from the NFA on that input. Yeah, so you just keep track of which states you can go to, and if you can't go anywhere, then you would just go to the empty set state, which is a valid set of states. Other questions? Okay, new topic. So when we were talking about languages, and I tell you on like your homework or something, like, let's just look at this example. So I think this is from your homework. I'm not sure. So it's the set of strings from 0, 1 star where W starts and ends with the same character.
It just starts.
What's sorry?
It just starts. That's fine.
I'm not sure what the problem is.
Like it
No,
doesn't
no.
matter.
There was no end, but that's fine. It's just W starts with 0.
Okay. This is the one I'm talking about. Okay. It honestly doesn't matter. So I'm just trying to describe a language. We're not going to make the DFA for it or anything, but I just want to talk about the language itself. So this seems pretty straightforward. It's the set of all strings such that some property holds. W starts with and ends with the same character. Is the string 0 in L? Is the empty string in L? Well, it seems reasonable that the empty string's not in there, right? Because starts and ends with the same character implies that the string is non-empty. There is a character there. But 0 and L, some people might interpret that to mean, well, the string has to have at least 2 characters. Well, 0, the one character is the same character that it ends with. So you could interpret that to mean that it's in this language, but there is some ambiguity as to what the language exactly means. So we don't necessarily know whether it's in L. Could there be a formal way of describing the language, the set of strings that of this regular language? Is there a way that we can describe the language in a formal way instead of just using English, which is not formal? So that's something that we're going to talk about now, which are called, you probably have heard of this, regular expressions. So the goal of a regular expression is to describe a regular language in a formal way. That's all it is. Okay. So how many of you have ever used a regular expression before? Okay. That's fine. So they're used for input validation on a website to check if, say, you have a registration form and there's a field for you to enter an email address for registration, then there are many different formats that you could have for an email. You can have someone at someaddress.com, or it could be .edu, or it could be something dot something dot something dot something. So there are many different formats that you could have here. So a regular expression is just a really formal way and precise way of describing the language itself. So what is a regular expression? So this is a definition here. So we say R, so R is the name, is a regular expression. If R is one of the following. And there are 6 different possibilities that R could be. Yes, 6. So, yeah, it seems quite a lot, but it actually makes sense for what we're trying to do here. So if we're trying to describe the regular languages, we we need to be able to describe all of the regular languages. So what are the smallest regular languages that we know of? So what's the smallest possible regular language? Even smaller. The empty set. So if R is the actual string, the empty set, then that's a regular expression. But the other suggestion about the empty string, that's also a regular language that we want. So on the right here, I'm going to put the corresponding regular language. So here it's just empty set. If R is equal to the empty string, then the language that we want with that is the set which has that one string in it. That's also a completely valid regular language because you did it on one of your quizzes. So it's a regular language too. What about not just a set with the empty string in it, but a set which just has a single character, where that single character is a member of the alphabet? Is that also a regular language? Yeah. Let's actually, because it's actually good practice, and it'll jumpstart on a result we're going to prove anyway. So these are the languages that we want. Let's make a DFA or an NFA for each of them. So what would be easier, a DFA or an NFA to make for a language? Well, every DFA is an NFA. So I think NFAs would be easier because we can just leave out transitions we don't need. So how can I make an NFA for the empty set?
Just have a single state where it's just not an accept state and then there's no transitions.
Yeah, super easy. Single state, no transitions. Could it get any easier than that? Oh, what about the next one, the empty string? That's the only string I want to accept. Well, with the DFA, we had the start state, which is an accept state, and then any character goes to another state. Could we do something even easier with an NFA? Yeah, what could we do?
It's only the entrance state and it's accepted.
Exactly. Nice. Are DFAs or NFAs easier?
Conceptually, DFAs.
NFAs are way easier. Okay. For the third one, the regular expression would be if it actually is that character, then it represents the NFA. The set which has that one character in it. What would be the NFA for just a single character and nothing else? I don't think we can get away with one state, unfortunately. Because if we had a self loop, then we can accept the string with 2 A's or 3 A's or whatever. So how can I do it with, say, 2 states?
The start state doesn't accept, and then you transition on that character, and that's the accept state.
Yeah, that's the accept state. Cool. Nice. So are there any questions so far? So the final 3, so you can think of these 6 possibilities as the first 3 are the base cases, and the last 3 are the inductive cases, the recursive cases. So the first 3 are the smallest regular expressions we can ever make. The next 3 are building off of smaller regular expressions. So there are 3 options here. Is there a set of 3 operations that we have recently talked about? If so, what are the names of those?
Union, and union,
Union,
concatenate,
concat, and
star.
star. What are those called?
Regular
The regular operations.
operations.
Cool. So if R is R1 union R2, or R is equal to R1 concat R2, or R is equal to R1 star. Then those are regular expressions too. If R1 and R2 are also regular expressions, then if you union two of them with an actual character union, then that's also a regex. If we just paste them together, that's also a regex. If you put a star with parentheses around one, that's also a regex. The language would be the language of the first regular expression union the second. The fifth one would be L of R1 concat with the language of R2. So there's actually no surprises here. So for the star, it would just be the language, the whole thing star. So it really encodes what the operation says. Union really does mean union. Concat really does mean concat. Star means star. No surprises. What about for the NFA version of it? Well, did we figure out how to union two NFAs together? Yeah, what was the idea there? Yeah, make that new start state epsilon your way to the original two start states. What about for concat? Did we do concat with NFAs? Yeah, what was the idea?
You had one NFA, you changed the final states to be not final states,
Mhm.
and you had epsilon transition to the next NFA.
From the original final ones. Yeah, so you just make the first one's final states no longer final. The original final states of the first one, epsilon your way over to the start state of the second one. And then star was kind of similar. We had that new start state and epsilon from the final states to the start state. So we've already actually done these. Oh, wait. So does that tell us if we have a regex, can I make an equivalent NFA for it? No, just an NFA. Can I make an equivalent NFA for it? Yeah, because whichever one of the six the regex prescribes to, we have a procedure to make the NFA for it. Cool. So that actually tells us that, so here's a little theorem here. Every regex has an equivalent NFA. And thus, its language is regular. Sweet. Getting a theorem for free. That's pretty nice. So let's actually do an example because quite a few students mess this up, even though it seemed kind of simple because there are some gotchas that you need to just think about. The key here is if you want to actually change a regex to an NFA, all you have to do is just follow the procedure exactly. That's all you have to do. You don't have to think about like trying to optimize several things. Just follow it precisely. So let's do an example. Oh, we're out of time? We're out of time, so we'll do the example next time.